So it sneaks up on you. You're taking a shower, and all of a sudden you realize that your water pressure sucks. And then you see that white, crusty buildup on your shower head. Sometimes you see it on your sink faucet. Oh, and sometimes you see a chunk of it floating in your cup of tea. I love that stuff. I'm a geologist, and the stuff that makes up that crust is called carbonate. Carbonate is dissolved in your water, so as water passes through your faucet or through your shower head, it leaves a little bit of solid carbonate behind, a very thin layer that you can barely see, but layer upon layer upon layer builds, and it becomes a huge pain in the butt. This process happens in the ocean as well. For example, coral skeletons are also made of carbonate, and they grow layer by layer. And we can use things like corals and the layered effect of it to learn about environmental conditions all over the world, including as far north as the North Pole. So the important thing here is oxygen. Carbonates and water both contain the element oxygen. And oxygen is powerful because it's not all exactly the same. There are different types of oxygen. And the ones I look at are different isotopes, so they have different weights. Oxygen 18 is the heavy weight. Very heavy. Oxygen 16, by comparison, is light. And we can measure the ratio between the heavy and the light one. So we all know that a lighter thing is easier to pick up than a heavier thing, right? Well, this happens on the atomic scale as well. When water evaporates from the ocean, to turn into clouds, it pulls out as much oxygen 16 as it can because nature is lazy and it wants to pick up the lighter one. And so an environmental way we apply this is during ice ages, all of that water vapor turns into clouds, and a lot of that ends up dumping out snow in the northern hemispheres. That snow comes down, and it turns into glaciers, and those glaciers build up and build up and build up, and they're super greedy. They just hog all of that oxygen 16. And then the water is left with a lot of oxygen 18. These corals that grow in the water, that layer of carbonate grown at that time is a snapshot of what the water looks like chemically. And that is enough to tell geologists what was happening up in the northern hemisphere. We can track the ice ages in this way. And a very little piece of carbonate, maybe a slightly bigger piece, but a piece of carbonate like this size can tell us a story that lasts hundreds, thousands, if you put them together, maybe millions of years. So when I see a crusty sink faucet, I see the environmental conditions in my plumbing. But if you don't like it, here's a tip. Carbonate dissolves in weak acid, so just get a jug of vinegar and you'll be fine.
Thanks, Gabriella. Thinking about the oxygen, you talked about how heavy isotopes get left behind instead of light isotopes. Is that true the world over? Is there variance between at the equator or in Antarctica?
Yeah, it's not quite as simple as I made it sound. There are a lot of things that affect which oxygen gets incorporated. So temperature has an effect, the temperature of the water. So usually corals grow in like a tropical region, so that tends to be more consistent on a large scale, but there are variations in temperature that we can track within those small regions. And also things like a heavy rain you'll dump a lot of the oxygen 18 out first when it rains, because it's heavier, right? And if you have a heavy rain, it dumps the oxygen 18 and then also the oxygen 16, which you could see in like soils that filter through and end up in a cave. But if it's a light rain, you're only going to get that oxygen 18. You're missing that oxygen 16. So there's a lot of really subtle ways we can use this depending on what environment we're looking at.
So it could help us to reconstruct environments or...
Yes, we can reconstruct environments on a lot of different time scales, on very short time scales, on very long time scales. It's all about what type of environment you're looking at, what type of process you're looking at.
Wow, that was a really beautiful explanation of that process. I've never thought that glaciers were jerks before, but now I'm like...
Yeah, they're pretty rude, yeah.
And I'm going to watch CLR infomercials now and not turn the channel.
No, but it's a ripoff. Just get some vinegar. That's all you need.
All right, so my question for you is, since that was such a great explanation of this very broad process, what is your specific area of research that you do using that?
Well, so in undergrad, I did some work on oxygen isotopes. And so we were looking at the environmental conditions of this water out down in Florida, off of the coast of Florida. And so there was this mass die-off of corals, and we were trying to look at this one coral that had survived it and tried to find out what the environmental conditions were through this survival period and whether or not that you could tell if that creature was really resilient to those sorts of environmental catastrophes. I was an undergrad, so I didn't get anywhere close to that. But those were the goals, right? And then for my graduate degree, I actually look at carbon isotopes in carbonates, which are a whole different ballgame, but tell you a lot of interesting things as well.
So I'm still in the ocean because something you said just suddenly made me go, I'm putting together pieces. You said that a weak acid dissolves the carbonate.
Yep.
And that's what these coral reefs are. Is there concern that we all hear about acid rain and all of that. Is that part of what's creating a problem with coral reefs?
Yeah, the specific thing that's causing the ocean to be more acidic is the exchange of carbon dioxide in the atmosphere with the ocean. So if you have more carbon dioxide in the atmosphere, eventually you're going to get more in the ocean, and that makes it slightly more acidic. So it is a concern in terms of all these creatures that grow shells and skeletons out of carbonates, their ability to be able to survive in a more acidic environment. There's a lot of research into it because life is really resilient. In Jurassic Park, life finds a way. They started to find that they have mechanisms by which they can protect themselves from losing their shells, but we don't know the extent of that and how far it will go. It's just too big of a system for us to be able to predict what's going to happen. So all we can do is make a difference in the future and just hope that they can figure it out.
And be grateful that we have an endoskeleton.
Yep. Thank you very much.